Hi guys, welcome back to my channel again. Today I'm really excited to make the request video for the first time in my channel. Some of my viewers and subscribers, they requested me to make a video on Latin square design and how to analyze data from the experiments that has Latin square design. So what I will do is I will show you my screen. I'll share you my screen and then I will show you how to analyze data from Latin square design, first using Excel and then using SAS. Alright, let's get started. So to understand Latin square design, you first have to understand what is CRD, that is completely randomized design, and what is RCBD, that is randomized complete block design. So if you look at this picture, there are four treatments in different plots. Four treatments are A, B, C and D, and you can see here there is no pattern at all. So this treatment A is here, here, here and here. I don't think you can notice any pattern. B again is here, here, here and here. There is no pattern again. And C is here, here, here and here. I don't think you can notice any pattern. And D is here, here, here and here. So CRD is completely random. Experimental units are randomly allocated to the plots. So there is no pattern, that is completely random, and you can't have any other factors apart from treatment. Because that is completely random. And if you see this randomized complete block design, you can see here now there is some pattern. So pattern in the sense that it looks like the plot is divided into four blocks. So block 1, block 2, block 3 and block 4. And you can see here block 1 has all the treatments A, B, C and D. Block 2 also has all the treatments A, B, C and D. And block 3 has also all the treatments A, B, C and D, and block 4 also has all the treatments A, B, C and D. So that means every block has all the treatments allocated randomly. So CRD had all the treatments allocated randomly without any direction, but RCBD has treatments allocated randomly to each block. So that means each block has all the treatments. And now next is Latin square design. And here you can see there is a double pattern. So if you compare this RCBD to Latin square design, so it looks like each row has all the treatment and each column has all the treatment. So let's go row by row. So row 1, this is row 1. It has A, B, C and D. Row 2 has A, B, C and D. Row 3 has A, B, C and D. And row 4 has A, B, C and D. And again column 1. So this is column 1. Column 1 has A, B, C and D. Column 2 has A, B, C and D. Column 3 has A, B, C and D. And column 4 has A, B, C and D. So the only difference between RCBD and LSD is LSD has double blocking, RCBD has single blocking. So LSD is basically the modified version of RCBD where you have double blocking. So RCBD only had block in one direction, either row or either column, but LSD has block in both of direction, both row and column. And the interesting thing with LSD is number of rows should always be equal to number of column. So as you can see here, because there are four treatments and each row should have all the treatment and each column should have all the treatment, that means you need to have row equals to column, otherwise you can't make LSD. So the example experiment would be impact of 4 diets on output of the cows. So for example, there are 4 cows and there are 4 treatments, and cow here is a row, and period, let's say week 1, week 2, week 3 and week 4 is a column, and there are 4 treatments. So that 4 treatments should be equally allocated to each row and each column. So that means we need to have 4 cows and we need to have 4 periods, 4 weeks. So this cow has all the treatment A, B, C and D. That cow also has all the treatment A, B, C and D. And that cow also has all the treatment A, B, C and D. And similarly, this week has all the treatment A, B, C and D. This week also has all the treatment A, B, C and D. This week also has all the treatment A, B, C and D. Similarly, the other example would be impact of 4 different environment on workers' performance. So there are 4 different environment A, B, C and D again, 4 workers and 4 week. and each week and each worker has all the treatments. But the problem with Latin square design is when you start doing the calculation, the error degree of freedom is too low. So what you can do is you can repeat the experiment or increase the number of rows and column to improve that. So for example, if you repeat the experiment, so this experiment, and again repeat that might also help you to improve the error degree of freedom. Or also what you can do is you can make column constant. So make column constant, this first column, second column, third column and fourth column. That means make period constant and increase the number of rows. For example, in the first example there were 4 cows, so you can make 8 cows or 12 cows and do Latin square design for each group. So first 4 cows Latin square design, second another 4 cows Latin square design, and another 4 cows Latin square design. Or what you can do is you can have 4 cows but you can increase the period. So Latin square design for 4 weeks, another Latin square design for next 4 weeks, and another Latin square design for next 4 weeks. So to analyze CRD, this is how the ANOVA table looks like, where you have source is treatment and error, and that is a total. So degree of freedom is treatment -1 and total degree of freedom is total experimental units -1. And I'll show you how to calculate sum of square later on in Excel. And then this is the formula to calculate MS, mean sum of square, and you can calculate later on F value. And then this is how you calculate ANOVA for RCBD. So where you have treatment, block, error and total, that is a source, and that is a degree of freedom, that is a sum of square, and that is a mean sum of square, and that is F value. And then this is a analysis of variance ANOVA for Latin square design. As you can see here, there are treatment, row. So row in first example it was cow, and column in first example it was week. So row was cow and column was week. And then there is a error or residual, and then there is a total. So these are the degree of freedom, and these are sum of the square, sum of square for treatment, sum of square for row, sum of square for columns, error sum of square, and then these are mean sum of squares, and that is a F value. And you already know that if F value is greater than tabulated F value, then you have a difference between treatments. So let's move down to Excel, where I will show you how to calculate ANOVA for Latin square design. So this is our Excel, so where we want to know the impact of 4 different diets, that is A, B, C and D, on the output of 4 different cows. And this is a Latin square design where you have 4 treatments, 4 cows and 4 weeks. And each cow has all the treatment A, B, C and D. Again A, B, C and D, A, B, C and D, and each week has all the treatments A, B, C and D, A, B, C and D, and same goes for week 3 and week 4. And that is the raw data. So raw data is like that. So that is the output. So output for cow 1 for week 1 for treatment A is 16. Similarly, output for cow 2 for week 1 for treatment B is 14. So I have given green color to treatment A, red color to treatment B, gray color to treatment C, and blue color to treatment D. And that is our raw data or output. That output could be anything. For example, milk or milk yield or milk protein or anything. And that is our raw total. So which is basically the sum of week 1 raw total, week 1, that is sum of week 2 if you click here, and then that is a sum of week 3 if you click here, and then that is a sum of week 4, and then that is a column total. So if you click, so that is cow 1 total, that is cow 2 total, that is cow 3 total, and then that is cow 4 total. And then this is a week 1 square, so which is basically a square of total of week 1. Similarly, square of total of week 2, if you see here 55.7 square, and then same goes for week 3 row square, and same goes for week 4 row square. And again same goes for here. So that is a column square, that is square of all sums of cow 1, that is square of all sum of cow 2 if you click here. So 58.9 square is 3469.21, and same goes for cow 3 and same goes for cow 4. And this one here is basically the sum of all the output, and as you can see here, that is a row and that is a column, and row is cow, so all row, and column is week. And this is basically the square of the raw data. So 16 square equals to 256, 14 square, so that is that, 14 square equals to 196, 13 square equals to 169, and 12 square equals to 144. So this square is going here. And then I again summarized this here. So that is a raw data for treatment A. So 16, treatment A has output of 16, 17, 17.5 and 18, which is here 16, 17, 17.5 and 18. And same goes for treatment B, same goes for treatment C, and same goes for treatment D. Because I want to calculate ANOVA using Excel manually, I need to do all this calculation. So that is a treatment total, which is basically sum of all treatment A, that is sum of all treatment B, that is sum of all treatment C, and that is sum of all treatment D. And that is basically treatment square, which is a square of 68.5 here. This one is a square of 55.1. This one is a square of 52, and this one is a square of 52.3. And that is basically a treatment mean, which is basically average of treatment A, that is the average of treatment B, that is the average of treatment C, and that is the average of treatment D. And that's a experimental total, which is basically this value. This is basically sum of everything, which is used to calculate this correction factor. So this correction factor is basically K21, that is experimental total square divided by 16. 16 because there are 4 rows and 4 column, and 4 by 4 is 16. So experimental total square divided by row multiplied by column is called correction factor. And when you calculate row sum of square, that is basically cow sum of square as well. In this example, cow sum of square is basically sum of all the squares of row divided by 4, because there are 4 rows, and that is subtracted by correction factor. And same goes for column, which is basically sum of all columns divided by 4, because there are 4 columns. If there are 5 columns, then it will be divided by 5. If there are 6 columns, it will be divided by 6, and same goes like that. And that is subtracted by correction factor. And here is the total sum of square. Total sum of square is basically sum of that, which is sum of this square, total sum of square minus correction factor. And treatment sum of square is basically total treatment square sum divided by 4, because that is 4 treatment, that has 4 treatment, and minus correction factor. And if you see in this table, there are 4 treatments, and treatment degree of freedom is T minus 1, which is 4 minus 1, 3. And then row degree of freedom, that is cow degree of freedom, is row minus 1, which is again 3, 4 minus 1. And column degree of freedom, which is week period degree of freedom, is C minus 1, which is again 3. And total degree of freedom is 4 by 4 minus 1 is 15. And error degree of freedom is total degree of freedom minus column minus row minus treatment. So 15 minus 3 minus 3 minus 3. And then this is an ANOVA table here. So I already showed you how ANOVA looks like in, I think, 2-3 minutes before. And so that's a treatment, that's a cow, row or cow, and then that's a column or week, and then that's error, and that's total. So degree of freedom is basically 3 for treatment, 3 for cow, 3 for week, and total is 15, which is 4 square minus 1, and then residual degree of freedom is 6. so that's what I was saying to you guys. So residual error degree of freedom is quite low here. So if you want to increase it, either you have to increase the number of cows and number of week. That means there will be more treatment, 5 treatment or 6 treatment or 7 treatment, or you have to repeat the experiment, or you can make a crossover kind of design, making either row constant but increasing the column, or making column constant and increasing the rows. And that's a treatment sum of square, which is basically that value which I showed you how to calculate that, and that's row sum of square, which is that value, and that's column sum of square, which is that value, and then that's total sum of square, which is that value, and error sum of square is basically this minus this minus this minus this. And then this is a mean sum of square for treatment, which is basically treatment sum of square divided by degree of freedom, and that is a mean sum of square for row. That is again same, row sum of square divided by row degree of freedom, and then again that is column mean sum of square, which is again column sum of square divided by degree of freedom, and that is residual mean sum of square, which is again residual sum of square divided by degree of freedom. And then finally this is a f value for treatment, and we are only interested in f value for treatment because we want to see whether the f value whether treatments are different from each other. And to calculate f value for treatment, so that is v13 by v16. So v13 is mean sum of square for treatment divided by mean sum of square for error. So 15.24 divided by 0.24, which is basically 63. And so this is our f value for treatment is 63, which is greater than tabulated f value. So to calculate tabulated f value, you can use this. So at 95, at p value 0.05, and numerator degree of freedom and denominator degree of freedom. So numerator is treatment and denominator is error, which is 4.57. So as you can see here, f value for treatment is greater than tabulated f value. So 63 is greater than 4. That means there must be a difference between treatment. But there are 4 treatments, so we don't know which treatment is different from which treatments. And I'll show you how to do that in SAS. So this is our SAS screen, guys. I have used SAS University Edition, and this is my raw data. So basically there are 4 cows, 1 2 3 4, 1 2 3 4, 1 2 3 4, 1 2 3 4, and 4 weeks. 1 week, week 1, week 2, week 3, and week 4. And then there are 4 treatments: A, B, D, C, C, A, B, D, D, B, D, C, A, D, C, A, B, and that is the output. So first what you have to do is you have to write data and what is the name. So you can give data LSD because that is Latin square design, and this statement always should be there for SAS University Edition, otherwise it doesn't work, it doesn't read the data. And our input is, first is cow, second is week, and third is treatment. So TREATM, let's do TREATMENT, and you always need to put $sign because they are in alphabet, not in number, because A, B, C, D, something like that. And then our output. So on the 4th column is our output, and then you can write cards and then give that and after the end of data give that semicolon. And then we are using proc GLM procedure, so let's write proc GLM. You can do mixed and glim mix as well. In the future video maybe I'll show you how to use proc mixed and proc glim mix procedure. And then our class is cow, week, treatment, and again semicolon. And our model is, because you want to know the difference, you want to know the effect of treatment on output, so output equals to treatment, and then means treatment. You can do means or ls means, and lines to key, because you want to see the difference between each of the treatment. And then let's do run. So click here. Perfect. So there are 16 observations, there are 4 treatments, there are 4 cows, and there are 4 weeks. And that's the model EF value, and then that's the treatment EF value, which is 17.65. so I will change little bit here. So if we add, what happens if we add cow and week, there might be slight difference in the EF value. Again, let's run. So now you can see all the degree of freedom and sum of square and mean sum of square for cow and week. Previously you couldn't see because I didn't add that in a model statement. Now I added. So that is a treatment, that is overall ANOVA, and that is a ANOVA for treatment, cow and week. So treatment has 3 degree of freedom, cow has 3, and week has 3, and that is type 1 sum of square for treatment, sum of square for cow, that is row, and sum of square for week, that is column, and that is mean sum of square for each of them, and that is EF value for each of them. And you can see here EF value, this is the EF value, and probability is less than 0.05. that means there is a difference between treatment. And if you go down, so that is a mean for treatment A, that is a mean for treatment B, that is a mean for treatment C, and that is a mean for treatment D. And it looks like treatment A is significantly different to all other treatments, as you can see here. So it says mean covered by the same bar are not significantly different. So B, C and D are covered by the same bar, which is red. So that means B, C and D are not different, but A is different from all others. So that means the output of treatment A was higher than output of treatment B, C and D. So A is either better or worse in terms of what kind of experiment you have conducted. So this is the end of today's video, guys. Please do not forget to like and comment on my video, and also feel free to share my videos so that others can benefit from it. And also please do not forget to subscribe to my channel. I'll see you again in next video. Bye. Thank you for watching my channel.